Okay, so good morning everyone. Let's get started. So we'll start with some new materials. That's going to be on what is called the feedback theorem. You have hopefully seen that there is a new draft chapter posted on D2L on this particular topic. And so I would encourage you to look through that chapter. It is a draft chapter. There's going to be further changes and trims to it. But if you have any feedback on the material of the chapter, I'd appreciate hearing that. Before we launch into the feedback theorem topic, from last time, I want to wrap up this quick discussion about the way we are going to use SPICE. In the class, we briefly discussed different types of SPICE analysis last time. And one key conclusion was that if we simply model the switching converters as they are, provide the models for the circuit as is, without any averaging or any other anything else applied to them, then those models are models of time-varying nonlinear circuits. They can be solved in a SPICE transient simulation, but all other types of SPICE simulations that we find normally useful in analysis and design of analog or mixed signal circuits do not really apply. Operating point, DC sweep, DC transfer function, or AC analysis do not apply. Do apply, but do not give meaningful results because the converter circuits are time varying. So the core segment that's going to come just after the feedback theorem is going to actually look into this particular aspect, and we will use averaging techniques and the circuit averaging and average switch modeling techniques to address those issues. As an example, this is a SPICE model of a complete switching converter with feedback applied around it. This is the same example that you have as part of your homework 1 assignment. The main purpose of that assignment really is to provide the encouragement for you to download LTspice if you haven't done that before, and run it. Run the simulation and see how things work. Play around with the menus and so on. So let's take a quick look at this circuit here. So here's the input voltage on the left-hand side. The input voltage here is given as 5 volts. We can recognize the synchronous buck converter, where we have 2 power semiconductor MOSFETs switched in a complementary manner. Then there is an LC filter. The circuit model does include the series resistance of the inductor L1, and it also includes the ESR resistance of the capacitor. In fact, the values in this example here are the same values that we used in the review lectures last week to illustrate the notions of averaging and the small signal modeling and transfer functions. Okay, this is basically the same numerical values. At the output, we have a load circuit, and then there is always a question of how do we actually model the load. And in many cases, we don't know exactly what the characteristics of the load are. In this particular case, we model the load as a parallel combination of some load resistance, here shown as 1 kilo ohm, in parallel with a current sink that models the current taken by the load, which in this particular application example could be a microprocessor. And so here you see that load is modeled actually as a pulsating current source that goes between 0 amps at the beginning to 5 amps at 150 microseconds. So we're going to be able to examine a step load transient response in the circuit. At the output of the converter, we have sensing of the output voltage. The sensed output voltage is compared to a reference. Reference here is shown simply as an independent voltage source. In reality, you can go certainly deeper into modeling the reference itself, which would typically be implemented using band gap techniques. If you take an analog IC design class, you will learn how to do that. Here, we are going to simply model that reference source as an ideal voltage source that's called V reference. And when you look at the detail of that source, you see that it's actually modeled as a piecewise linear source that starts from 0 volts and then reaches a value of 1.8 volts after 50 microseconds. So in time domain, the reference as a function of time would look like this. So if this is the reference right here, you would ramp up in a matter of 50 microseconds and then have a flat value of 1.8 volts after that. What is the meaning of this particular setup? Why are we doing this? Well, first of all, if I were to ask you a question, what is the reference really for this voltage regulator? What would be the answer to that question? What is ultimately the voltage we want the output to be regulated to? 1.8 volts, right? And in the simplest of all cases, you could just give a DC voltage source of 1.8 volts right here, right? That's what you could do. Why are we doing this stuff right here? Why were we ramping this gradually from 0 to that 1.8 volts? Because in reality, switching converters are actually complicated things. And if you immediately apply a 1.8 volt upfront reference and everything is at 0 and you start switching, you would see a large inrush of current at the beginning with the converter trying its best, pushing the duty cycle to the limit in order to try to bring the output voltage to regulation as quickly as possible. That often results in transients that are not desirable. You may have an overshoot in the output voltage that would be prohibited by the nature of the load. You may damage the load in the process and so on. So this particular ramp up gradually of the output voltage is commonly referred to as soft start. So this is one version of what is called soft start technique, implemented here through actually just gradually ramping up the reference from 0 to the final value of 1.8 volts. Okay. Then you see the sensed voltage right here, let's call this V out right there, is then compared to the reference. That's great. What do we do with that comparison? We process that through a compensator. And that compensator is built in an analog fashion using just resistors and capacitors around an operational amplifier. What type of compensator do we have here? There is an integral action because of this. So this is your I type thing. On the input side, you have this parallel combination of R and the series combination of a capacitor and resistor. That's going to give us a 0 and a pole. So that's going to be a PD action right here. And overall, this is going to be a PID compensator. This is exactly what we talked about in terms of transfer functions last week. In fact, when you actually compute the transfer function of this compensator, you will see the values of the poles and zeros match very closely to the theoretical values that we mentioned in the class last week. Then the output of that is going to be this V control signal. V control signal is the input to the pulse width modulator. There is a block that implements the pulse width modulation function. That block is provided in a library of components that's called switching.lib. So this line of lib, switching.lib has to be included in the circuit model to invoke models for the sub-circuits that are representing these different functions in the switching converter. And one of the functions we provide is a pulse width modulator. That pulse width modulator has parameters. The key parameters being the switching frequency, which in this case here is 1 megahertz, and the other parameter being the VM, right? VM is the amplitude of the sawtooth ramp. You can go inside the switching.lib library and look at the netlist for that sub-circuit that implements the PWM function and see the details of how that actually is implemented. Then the output signal right here is going to be a pulsating logic level control waveform with a duty cycle D being proportional to the control voltage at the input of the pulse width modulator. Okay, we understand that. Now, what do we do with that signal here? In the actual circuit, we do need another block that provides these dead times of ensuring that the two power MOSFETs are not turned on at the same time. So this block right here is called the dead time circuit. That dead time circuit splits that signal C into two complementary signals, C1 and C2, with gaps between them. So if you look carefully at C1 and C2, and I'd encourage you to do that when you actually run the simulation, you would see that they actually look like this, with small gaps inserted between the conduction of MOSFETs 1 and 2, and those gaps are called dead times. All right. The dead time circuit has a parameter that lets you choose whatever dead time you like. In this particular case, we have a dead time of 30 nanoseconds. So TD is 30 nanoseconds. The way the subcircuit is constructed, it assumes the same dead time of both commutation events. All right, now we have C1 and C2. Those are still logic level control signals. We then pass them through gate drivers. And those are the gate drivers you have right here. And you see we have two gate drivers, one for each MOSFET. The low side gate driver shares the same ground as the ground of the power MOSFET. The upper side gate driver does not. The upper side gate driver has the purpose of level shifting that control signal to the upper side MOSFET, because this node right here is moving up and down between 0 and the input voltage. And so the upper side gate driver requires the function of really being able to level shift the control level signal with respect to ground to a gate to source drive signal with respect to the source of the MOSFET M1, and that source is swinging up and down as the MOSFET M1 and M2 are switching. Okay, so to provide that function, a typical driver for the high side MOSFET, this MOSFET M1 would be called a high side MOSFET, and this driver here would be called a high side driver. That driver can be implemented in any number of ways. One way is to use what is called the bootstrap technique. So you basically have what is equivalent to an auxiliary power supply that floats up and down together with the switching node right here. And that function is provided by this energy storage capacitor C sub B. That capacitor is charged up through this auxiliary Schottky diode whenever the switch M2 is on. So when you turn the switch M2 on, you charge up the capacitor CB to the input voltage. And then when you have the opposite case, when M1 is on and M2 is off, that CB floats up and holds the supply voltage necessary for the driver. So the driver has the ability to provide gate to source voltage of M1 to keep it on in the on state. Okay. All right, so that's it. That's again just a very, very quick summary of the circuit that you have a chance to, is given in the homework assignment. Take it and do the assignment, but I would also encourage you to poke around a little bit and learn how various sub-circuit blocks here work. Look at the signals here, C1 and C2. Look at these gaps right here that we are forming. Look at the function of the pulse width modulator. Go inside the library and examine how these sub-circuits are actually implemented. You will, I think, gain quite a bit from spending a little bit more time on this exercise here rather than what is strictly required by the homework assignment. We'll be doing a lot of simulations, and it is good to be really familiar and up to speed with using the tool. All right. And so in this particular case, we just run a transient simulation, right? So a transient simulation, notice that the output voltage is in fact ramping up. It's ramping up because the reference voltage is ramping up. In that ramp up process, the control voltage has a spike at the beginning to boost up the current quickly. As the output voltage is then approaching the reference, which is 1.8 volts right here. Here we are in regulation. This is 1.8 volts right here. Initially, we have very little load current, and so the inductor current from this charging up the output filter capacitor is going to go down to value that is swinging around 0. On the right-hand side, you have the vertical scale for the current, so you will see 0. The current is going up and down around 0 when the load is very low. But then at this point right here, our load current steps abruptly from 0 to 5 amps, and as a result, you will see a little dip in the output voltage. It's not perfectly regulated. It is very well regulated, but not perfectly. And your homework assignments ask you to see how large this drop is going to be right here. So I'm basically asking you to zoom in on this waveform right here and find out how large this delta V is going to be in response to 0 to 5 amp step load transient. Look at what happens with other waveforms. When exposed to a step load transient, what is the feedback loop doing? It's trying to regulate the output voltage, and to do so, it's bumping up the control signal very quickly. That's what the PID compensator does for us. It has this quick action responding to a drop in the output voltage to boost the duty cycle command up. The duty cycle command actually saturates at close to 1 right here, and the current ramps up fairly quickly. You can see that in the response for the inductor current. This green waveform is the inductor current. And then finally, we do get back to steady state voltage regulation. At this point here, we have the average value of the inductor current equal to 5 amps. Okay, and then we have the opposite transient, moving back from 5 amps down to 0 amps, and you have the opposite type of action happening in the converter with, again, there's going to be some delta V right here. The homework 1 assignment asks you basically just to find this first one, right? So when you have a 0 to 5 amp transient, how much does the voltage drop, how much the voltage drops in response to that transient? Okay, so I think this is probably all I wanted to say about this very quick introduction to using SPICE to do transient analysis of switching converters. A couple of main points is, again, to look at how the circuit is constructed. We are going to use these switching circuit blocks contained in the switching.lib library, and those include pulse width modulators, dead time circuits, gate drivers, and then of course you have a variety of components you can use as op-amps. You can use any passive components you like, and a variety of components you can use as power semiconductor devices. So we will be able to construct very realistic looking circuits in the class. Any questions about the SPICE intro? Have you had a chance to actually run the simulation so far? The homework is due on Thursday. This is one of the shortest homeworks, but it's not super short. You still need to do some work, right? So don't leave that for Thursday. Do it now, today, okay? All right, yes, you have a question.
So whenever you're selecting a dead time for the circuit, what all things do you need to consider to select the dead time? That how do I know that I need 10 nanoseconds dead time or 20 nanoseconds dead time?
Right. So the question is, where is this 30 nanoseconds coming from? How do we make that particular decision, right? So that's a very good question. So the dead time, again, really, what is the purpose of that time? The purpose of that time is to ensure that we don't have these two devices conducting at the same time. So you really go back from that purpose into how that time decision is made. Okay. So you want to find out really what is the application you're working at. And here, in this case, we have relatively low voltage and high frequency switching. We have fast switching devices M1 and M2. When you look at the transient waveforms of what these devices M1 and M2 are capable of doing and how fast transitions we observe at this switching node, you will see that those would be in the order of maybe 20 nanoseconds or so. Now that does not mean that's always going to be the case. If you look at a 400 volt type switching with very different devices and much longer transition times, you may want to have dead times in the order of a few hundred nanoseconds, right? So it is very much application detailed circuit design oriented. Okay. Now you can say, well, if the only purpose is to have no simultaneous conduction of these devices, why don't we just play it safe and make that time be very long? We have here a switching frequency of 1 megahertz, period is 1 microsecond. I could safely put here 200 nanoseconds of dead time and everything would be just fine. You can give it a try. Why do we not want to have dead times too long? Well, if you make the dead times really, really long, you're never going to be turning on the rectifying device. But there is somewhere in between as well. 200 nanoseconds would not be too long with respect to the microsecond we have in the period. But it would still be too long from the practical point of view. Why?
But voltage would drop? Regulation voltage would drop?
A regulation voltage would drop is not necessarily the case. In fact, I would also encourage you to actually run exactly the same example with 200 nanoseconds of that time and see whether the voltage is still regulated at 1.8 volts. The magic of feedback comes into play here. No matter what detailed stuff happens right here, feedback is up to the limits, is going to be able to overcome that and still provide the output voltage regulation. What would be the key detrimental effect of having too long dead times? The main.
You'd have more body diode related conduction.
Yes, yeah. Remember the story of why do we employ the synchronous rectifier in the first place? We employ the synchronous rectifier because the forward voltage drop across that device is going to be much smaller than the forward voltage drop across a body diode or any diode that we could possibly put right here. So if you put a long dead time right here, that means you will have a longer conduction of the body diode and losses are going to go up. Okay. So dead time is basically, from the safety point of view, you don't want to short this circuit path right here. And from the losses point of view, you want to have it as short as possible. And in fact, if we had a different class, we would talk about ways to optimize the dead times. There are actually smart circuits that can do that in a variety of ways. But right now, we're going to stick to just a fixed choice of some reasonable dead time. All right, that was a good question. Anything else on this SPICE circuit?
How do we select the slope of the ramp when we start?
How do we select the slope of the ramp for soft start? That depends on how fast our feedback is. Okay, so you can also try playing with that a little bit. If you try to ramp up too quickly, you will see that the duty cycle stays saturated for a longer period of time, and you're going to expose your circuit to a larger overshoot. If you do the soft start too slowly, it's going to take a longer time to get to regulation. So there are practical trade-offs in that space. All right, enough. So play with this. Do more than what I asked you to do in the homework. And then right now we are going to start talking about the techniques of design-oriented analysis, in particular the feedback theorem. So it is a material that I think you will find quite interesting and useful in the design process. It has a name associated with it. The feedback theorem is attributed and it's really contributed by Professor Middlebrook at Caltech. It is a general approach to analyzing feedback circuits and systems as long as those feedback circuits and systems are linear and time invariant. And when we say general, it is a method that is capable of performing that analysis of feedback circuits in the cases that do not fall into the standard control theory block diagram form. In real circuits, it is very often difficult to actually put a circuit into a block diagram form. Sometimes we can do it, sometimes we can't. The feedback theorem allows us to actually do very quickly and relatively easily analysis of feedback circuits that don't necessarily form an easily identifiable block diagram. We can also allow the possibilities of having arbitrary input and output impedances, and we can also allow for the possibility of having the signal flow being bidirectional, as really is the case in real circuits. Okay. The derivation of the feedback theorem is based on the linearity assumption about the system, and it's going to apply techniques of superposition and something that you may have not seen. It's called the null double injection. Okay. I said at the beginning, the feedback theorem applies more generally to cases where we are not able to necessarily easily identify a block diagram. But when you do the derivation and you try to do that in a general sense, you have no choice but to resort to a block diagram as a representation. So that's a little bit of a contradiction right here. So notice that the starting point that we have in the discussion of the feedback theorem is in fact a block diagram, and we can identify a single feedback loop in that block diagram. Here's an input signal, here's an output signal. In the input to output signal, we have what we call a forward path. That forward path would be generally processing the error between the input and the sensed value of the output signal, whatever that may be. And that processed error signal is then ultimately passed to the output. In that block diagram, which I said is really an attempt to represent this in a general manner, we also have, importantly, a point that we are going to call an injection point. And I will remind you of the material you covered in the introductory class with respect to the measurements of loop gain. I'll refer to that in just a second. So we'll be looking at this block diagram right here as a generic form of a feedback circuit we would like to solve. What do we actually want to solve? When you have a feedback circuit of this type right here, what is the primary transfer function of interest? What is ultimately the end goal of any analysis of that system? Output over input. That's what we ultimately want. We want to find out a way to find what is the output over the input. Okay? And that goal is what we are going to keep in mind as we go through the feedback theorem. All right. So a couple of important points about this injection point. So we say there is an injection point that we can refer to as being ideal. Ideal injection point includes two aspects. One is that the signal uy, the signal right here, at this point right here, to the, if you wish, to the left of the injection point, is directly proportional to the error signal. So it is directly proportional to the error signal, and it's not directly affected by the injection itself. So in the sense of the measurement of loop gain, you have seen this particular type of setup when we use the injection signal to enable measurement of the loop gain. And in those sections 9.6.1 and 9.6.2, we noted that that injection signal can be a voltage injection signal or a current injection signal. And indeed, that is the case. That's going to be the case in the application of the feedback theorem as well. The way we put that in a more general form is to call this U sub Z, right? So U sub Z is, in a generic sense, an injection signal that could be a voltage type or a current type. Right. So the second aspect to the ideality of the injection point is that there are no alternative signal paths through the forward portion of the feedback loop other than what is shown right here. More specifically, if you set ux signal equal to 0, then none of the error signal is going to reach the output. So those are two characteristics that we associate with the ideal injection point. So number one, uy is directly proportional to the error signal. And second, there are no alternative paths. There is nothing that is bypassing this right here or going down right here. The forward path is as shown right here, and there is no way for the error signal to reach the output other than going through the path that is shown right here that goes through the point where the injection is actually made. So again, if ux is equal to 0, the output would be unaffected by the error signal. Okay. So let's see what the result of that feedback theorem is going to be. Before we do that, let's point to the fact that this is the system that has two independent inputs. Those two independent inputs being the input signal that we refer to as ui and the injection signal that we refer to as uz. Okay, so those are two independent inputs. The system has three outputs of interest. One is the output signal itself, and the other two outputs of interest are going to be this uy and ux. So in a block diagram form, you think of the feedback system that has two inputs, the actual input and the injection, and has three outputs of interest, those three outputs being the output signal itself and these Y and X signals around the injection point. Okay, so now we are ready to actually just state the theorem result, and then we are going to derive it. So the feedback theorem main result goes like this. So we said the main purpose is to find the overall closed loop transfer function. And the way the feedback theorem gives that result is in the following form. It says the overall transfer function, U naught over Ui, the output signal over the input signal, is equal to this expression, G infinity T over 1 plus T plus G naught over 1 over 1 plus T. Okay, great. But what are these individual values inside? So T is the loop gain. So when you look at the definition of the loop gain, is the ratio of the Y over X signals, Uy over Ux, when the input signal is equal to 0. This is definition of the loop gain. And in fact, it's exactly the same definition that we used earlier when we examined measurement techniques for feedback systems. So again, the loop gain is Uy over Ux when the input signal in general, could be voltage or current, is equal to 0. What are the other elements in this expression right here? A particularly important element, and the one that's very easy to give an intuitive interpretation to, is called G infinity. So let's look at the G infinity term right here. So G infinity of S is defined again as output over input, but not when the input signal is equal to 0, but instead when the Uy signal is 0. And you will be careful to notice this symbol right here. It's called null symbol. We are basically saying this is output over input when the Uy signal is nulled. We'll be careful to distinguish between having an independent signal equal to 0 or dependent signal being nulled. Those are two very different situations. So independent signal can be 0 or non-zero. A dependent signal can be nulled or not nulled. Okay, so nulling the Uy signal is the condition under which we evaluate output signal over the input signal, and that gives us the quantity that's called G infinity. The interpretation of that G infinity is that it represents the ideal forward gain. Why do we say that? If you go back to the block diagram right here, and you say, what happens if we null Uy? If we null Uy, that implies that the error signal is nulled as well. If the error signal is nulled as well, that means we have a perfect regulation. There is no error between the input signal and whatever is the sensed value of the output signal. So nulling Uy by this property of the ideal injection point implies that the error signal is nulled, which implies perfect ideal operation of the feedback system. In fact, in many cases, we design the feedback system having this G infinity, having the ideal response in mind to start with. So G infinity formally is defined as UO over UI when Uy is nulled. Now, there is another interesting G component right here that actually shows up right here. It's called G naught. So G naught, again, is the ratio of U naught over Ui. So again, output over input, okay? But when Ux signal is nulled instead, okay? Let's see what that really means in the block diagram. So we're saying, all right, what is UO over Ui when Ux is nulled? How can that be non-zero? You know, we already said, and the ideal injection point will be such that null, having Ux equal to 0 is going to have no error signal propagating through to the output. So if that's the case, if we null Ux, how could we possibly have anything at the output showing up at all? Why is this not just 0? Why is this G not 0 right away? Why do we bother with it at all? Because in reality, in real circuits, it is entirely possible to have signal propagation in the opposite direction. And that signal propagation can actually give G naught that's not equal to 0. And that's what we can evaluate. How exactly large that G naught is and what it consists of is again formally defined as a ratio of IO over I input when UX is nulled. Okay? And then there is finally yet another quantity that actually doesn't show up here directly in the expression that we are showing right here. It's called the null loop gain. Null loop gain, similar to the actual loop gain, is UY over UX, but under the condition that the output is nulled. Okay, so you see this actually looks a little bit of strange. We say, what is the loop gain when the output is nulled? It does not have so easy intuitive interpretation as the other three quantities do have. But there is an interesting relationship that's called the reciprocity relationship that actually links these four quantities together. So we will find out that Tn over T is equal to G infinity over G naught. Okay, so you will see that in some cases it's in fact actually easier to find Tn as opposed to T, and we can use the reciprocity relationship to then find the loop gain. So it could be a shortcut in the analysis process if you wish. So that's the main result. What follows next is really an attempt to derive where this main result is actually coming from. Stop here for a second and see if you guys have a question.
There you have put UI as negative in the previous block diagram, and why? Is that just for a convention or?
Right. So the question is why does UI why does it have a minus sign in front? This here is really by choice. It is a convention, right? So this minus sign here is so that we get a positive loop gain when the feedback applied is negative. It's just a choice, right? It is a choice right here. Nothing fundamental about that, but we're going to stick to that as being a definition of how UI is set up. All right? Any other questions? Yeah, this kind of goes top down, right? So you will see it hopefully will become more and more clear and useful as we go through it. But we do want to derive it first. We actually want to derive it formally, right? So the feedback theorem derivation steps, there are actually 6 steps that we need to do. And those 6 steps are going to be, first of all, finding or defining transfer functions when only input signal is present. That is going to define the system closed loop transfer function G. Then we are going to find the transfer functions when only the injection is present, and that's going to give us the loop gain T. We already know that, right? But let's do it in the context of the feedback theorem. Then the next step is very important. We are going to apply superposition and express all output quantities in terms of the contributions that we find in steps 1 and 2. Okay, so those are 3 steps that I think we would be able to do with just a basic circuit analysis knowledge. The steps that follow are a little bit unusual. They rely on what is called null double injection. I'll stop with that and try to explain it carefully. But you will see we'll actually have 3 such steps. So first nulling UY and finding expression for G infinity, then nulling UX and finding an expression for G naught, and then finally nulling the output U naught and finding expression for Tn, right? So let's go through these steps, right? So first, transfer functions when only input UI is present. So UI is present right here. In the block diagram, the injection signal is set to 0. It's not null. It's just equal to 0. It's an independent source. We just set it to 0. In the particular derivation step, we have the current injection used as an example. You could do exactly the same steps with voltage injection. No difference. So, well, first of all, let's see where the I sub z signal is actually injected. It's injected in parallel with a current source that represents the propagation of the error signal through this block, whatever it may be, and the output port of that block looks like a current source, like a control current source. That's an ideal injection point for the current injection signal because the IY signal is completely dependent on the error signal here. So this IY is going to be directly proportional to the error. It's not going to be directly affected by the presence or not of IZ. So that meets the conditions of the ideal injection point. Okay. The setup for the transfer functions when the input UI is present is that IZ is simply equal to 0. There is no injection. Okay? So what do we say then? The output over input under the condition that IZ is equal to 0 is what? That's G itself. So this here is the transfer function we are looking for. This is the definition of the transfer function we are looking for. What can we say about the other two outputs? You know, we have IX and IY here. What do you see for IX and IY? Well, IX is equal to negative IY. We can just read that from the diagram. And we can also say that IX is some function of the input. So we can say IX is equal to GA times the input signal, where this GA is, we don't know what it is right now. Okay. Right, so here's the summary of what we have so far. So we have IX is equal to negative IY is equal to some GA function, where we don't know what GA is right now. And we have U output under the condition that the injection is set to 0 is equal to G times U input. Very simple. This is just really restating the properties of the system when there is no injection present whatsoever. Now, next we want to do the step number 2 is to find the transfer functions when only the injection UZ is present. So we set UI to 0. There is no input present. You know, if it's a voltage source, it's a short. If it's a current source, it's an open. But we do have IZ present. The injection signal is in fact present. For this setup right here, we can say that IY over IX under the condition that UI is equal to 0 is equal to what? What is that? That's the loop gain. That's T. That is by definition T. T is IY over IX under the condition that the input signal is set to 0. And this is exactly the way you've been computing loop gain in any number of examples in the introductory class. So IY over IX under the condition that the input is equal to 0. What can we say about the IX and IY signals with respect to IZ? Well, see, we have that IX plus IY is equal to IZ. Now, you can then put this in any form you like. If you say, all right, IY is equal to T times IX, you can have IX 1 plus T is equal to IZ. And you can have that IX is equal to IZ 1 over 1 plus T, right? So you can do that. And then, of course, IY can be expressed in terms of IZ in a similar manner. So to summarize this particular step, here is what we have. So we have IY is equal to T times IX. And on the other hand, we can also express the output voltage as some other function. We don't know what it is right now. GB times IX, okay? So I naught is equal to GB times IX, or in terms of the independent input, the injection signal, that's going to be GB over 1 plus T times IZ. Where is that coming from? This part is coming from what we just found is that Ix can be found as Iz over 1 plus t, right? So this is basically just introducing yet another unknown transfer function, G sub b, into play. Next step is going to be superposition. Very simple. So we have two independent inputs, right? We have the independent inputs is ui and iz. And with respect to each one of them, independently, we have expressions for the outputs, ix, iy, and u naught. Now, it is a linear time invariant system, so we can certainly write these contributions together and say that in the presence of both independent signals at the same time, we have these general expressions for ix, iy, and u naught given as superposition of the results we had in steps 1 and 2. So this is superposition, and it comes from steps 1 and 2. Okay? So far, so good. Now, of course, this actually does look a little bit confusing because we are setting up definitions for these various transfer functions, but in the process, we had to introduce these two quantities, G sub A and G sub B. And those G sub A and G sub B represent transfer functions in the systems that are generally not of interest. They're auxiliary transfer functions in the process of deriving the feedback theorem, but ultimately, rarely we would care exactly what GA or GB really are. And so the remaining steps have the main purpose of eliminating GA and GB and putting everything in terms of these quantities that we do care about. Those are the remaining steps of the feedback theorem derivation, and those are going to be done through what is called null double injection. So null double injection is going to allow us to eliminate GA and GB in favor of the quantities that we do care about, and they're going to be relatively easy to find. And those are loop gain T, null loop gain Tn, the ideal gain G infinity, and this transmission through the feedback path is called G naught. Okay, so let's do that. So the null double injection is a topic that I want to spend a little bit of time on, just enough probably as we have through the end of this lecture here. So I'm going to give you an example right here and put it in the form of a null double injection so you can see what we're talking about. I'm going to put together a really, really simple circuit. Let's say something like this. I have two sources. Let's say this is V1, this is V2, two independent inputs, and then I'm going to have V output 2 and let's say V output 1 right here. Okay. And let's suppose these resistors are all exactly the same. All right. So I'm sure you can solve this circuit in 1 second, right? There's no problem with this. You can just put together these transfer functions, if you wish, from any of the inputs to any of the outputs very easily. But I'm going to ask you the question that actually does require thinking in terms of the null double injection. The question that we want to discuss right now is, what is V output 1 over V1? So V1 being the independent input, and what is the ratio V output 1 over V1 under the condition that the other output is nulled? Okay, that's what we want to discuss in the next couple of minutes. What do you say? Well, first of all, what does this nulling really mean? Okay, the most important thing to understand about the nulling is that the transfer function that we are looking for is found in the presence of two independent inputs present at the same time and adjusted so that a certain output signal is equal to 0. So let's put this in writing. So V1 and V2 are present and adjusted so that V output 2 is equal to 0. This is what we mean when we say V output 2 is nulled. That's what it means. You have to be really careful about this. So nulling a certain dependent output means that there are two independent signals present at the same time that acting together on the circuit result in that particular output being equal to 0. Nulling, most importantly, does not mean you're shorting that voltage to 0 or turning off some current to 0. It means setting it to value equal to 0 in the presence of two independent sources at the same time. Okay, so we null V output 2. So that means this voltage here is equal to 0. Let's suppose this is a ground, right? So this voltage is equal to 0. Can you tell me now what V output 1 over V1 is under that condition? How much current goes through this R? No current going through R because the voltage across it is equal to 0. That R is not shorted, okay? So there is no current going through it. Voltage across it is equal to 0. What is the current that flows through this R right here? It's V1 over R. Where is that current flowing through?
There are.
Through the other resistor right here. So this must be V1 over R as well. And so V output 1 voltage under the condition of nulling V output 2 is going to be equal to minus V1. And that's under the condition that V output 2 is nulled. So the answer to this question right here is V output 1 over V1 under the condition V output 2 is nulled is equal to minus 1. Okay, looks a little weird, right? You know, because you say, well, if you were careless about this and you don't understand the concept of null double injection, you say, well, I would just short V output 2, right? That's 0. It's very different. Because if you shorted V output 2, there would be no current due to V1 going through this resistor right here. That current would be totally unaffected by V1. It is affected by V1 because nulling does not mean shorting. It means setting it to 0 by independent action of two sources present at the same time. Okay, so we're going to apply this nulling now in 3 steps that follow and lead to getting the final result for the feedback theorem Wednesday. Okay.